Welcome everyone. My name is Vincenzo, and together with Dimitris and Bastian, I'm going to present this tutorial titled The Role of Event Time Order in Data Streaming Analysis. We all belong to Chalmers, University of Technology in Sweden. We belong to the DCS, the Distributed Computing and Systems Group, at the Networks and System Division, which belongs to the Computer Science and Engineering Department. Me and Marina work as associate professors. Dimitris is a PhD student, and Bastian is an industrial PhD student employed by Volvo Cars. This tutorial is divided in 4 parts. We will begin with some motivation and with an overview of basic concepts about data streaming and stream processing engines. We will then discuss why out-of-order data can be observed in streaming applications and how total ordering can be enforced. We will discuss the trade-offs when enforcing total ordering and conclude presenting other ways of dealing with out-of-order data with a special focus on watermarks. Before we start, let me also say that these slides, as well as code and data for the examples we will show in this tutorial, can be found at this link. And let's focus now on the data streaming paradigm in more detail. We are all familiar with the concept of big data and the unprecedented growth of data we sense and share. You probably have already seen some of these examples, referring to hours of videos uploaded to YouTube every minute, the amount of posts shared in social media, or the huge number of sensors we can find in the Internet of Things and cyber-physical systems. All this is not new, nonetheless, since data streaming was motivated by similar challenges back in the year 2000. Back then, when data streaming research started, the idea behind data streaming and stream processing engines, or SPEs, was to shift from a traditional first the data, then the query, to a first the query, then the data approach. As you know, traditional databases are designed to store data and read it back to memory only when a query is run. Despite the advances in storage systems, main memory is faster than persistent storage. With data streaming, the idea is to rely on continuous queries that do not read previously stored data, but rather ingest data as it comes in the system, updating their state and producing results continuously. Please notice that there has been a lot of research work and development of SPs in the last 20 years, of which this is an incomplete list. We cannot, of course, cover all that was done in detail, but we try our best to cover aspects that you can find basically in all these projects. Also, notice that in this tutorial, we decided to use Apache Flink for our examples rather than some other SPE, because Flink is one of the most used SPEs worldwide. In order to introduce the data streaming paradigm, the first step is to define what a stream is. In the streaming model, a stream is an unbounded sequence of tuples that share a common schema, which defines which attributes each tuple carries. In this example, we consider streams of reports from vehicles. Each tuple specifies the ID of the vehicle to which the tuple refers to, the time the report refers to, and the speed and coordinates of the report. This example shows a stream in which vehicle A forwards 3 tuples, one at 8 in the morning with speed 55.5, one at 8:03 in the morning with speed 70.3, and one at time 8:07 with speed 34.4. We assume for now that each vehicle produces and delivers tuples in timestamp order. What is important here is to understand the role of this time attribute, which represents the event time this tutorial is about. The timestamp represents the time at which each tuple has been created by the car in this example. Of course, there is no guarantee the tuple will be processed instantaneously. In other words, there is no guarantee that how time evolves at the computer running the analysis based on its clock is aligned with how time passes based on the timestamps of the tuples we process. This is important. The notion of time in streaming applications is usually carried by the tuples timestamps. In this sense, 1 year of event time could pass for the SPE in 10 work log seconds. For instance, if we are replaying past data at higher rate it was originally sensed. Once we define what streams are, we then define continuous queries, or simply queries in the reminder, as directed acyclic graphs of streams and operators. We have source operators that only forward tuples to other operators, operators that define both input as well as output streams, one or more of them, and sync operators that are fed the results of continuous queries. Sources and sinks can be considered as the entry and the exit points of a streaming continuous query. When it comes to the operators, we can distinguish them into two main types. On the one end, we have stateless operators. And as the name suggests, they do not maintain a state that depends on the tuples being processed. They process each tuple individually. On the other end, we have stateful operators. These operators maintain a state that evolves based on the tuples they process. Consequently, the results computed based on this state also depend on multiple input tuples. Map and filter are common stateless operators that can be found in an SPE. Here we can see some examples based on Flink. In the first example, we have a stream that carries integer values, and we feed such stream to a map. In this case, each integer is transformed in another integer by multiplying its value by 2. Some SPEs like Flink differentiate between maps and flat maps operators. The former transforms each input tuple into exactly one output tuple, while for the latter, each input tuple can result in an arbitrary number of output tuples. In this second example, we tokenize a string of sentences into a stream of words. Both streams are of type string. The last example is about the filter operator. In this case, we feed a stream of integers and only allow non-zero values to go through the filter operator. If we now move to stateful operators, we have the aggregate operator, which can be used to aggregate together tuples and compute functions such as max, min, or sum, and the join, which can be used to match tuples coming from two different streams. Here you have some examples of aggregation functions in Flink, and we will discuss later why they are applied to a keyed stream. Stateful operators bring us to the main topic of this tutorial, that of event time. Since streams are unbounded, we need to define the scope, that is the portion of data, over which we want to run some stateful analysis. This is because if we take a join as an example, we cannot really match a tuple from a stream with an unbounded sequence of tuples coming from the other stream. In data streaming, we usually rely on windows. The common windows are time-based and tuple-based windows. The former defines the scope of stateful analysis based on time, for instance, to aggregate all tuples received in the last 10 minutes, while the latter defines the scope in number of tuples, for instance, to aggregate the last 50 tuples. Notice that a time-based window has a fixed size, but the number of tuples it contains depends on the rate with which we get such tuples. On the other hand, a tuple-based window has a fixed number of tuples, but the period the latter span depends again on the rate with which we get such tuples. Since this tutorial is about event time, we will mainly focus on time-based windows from now on. This example shows a time-based window of size 1 hour and advanced 20 minutes. For such a window, a result will be produced for the window covering the event time period that goes from 8 to 9, one for the window covering the period from 8:20 to 9:20, and so on. As we explained before, the passing of time is based on the event time carried by the tuples, not on the clock of the machine running the SPE. The question we want to focus on now is, when is it okay to produce the result for a certain window? How do we know that we have processed all the tuples falling in such window? That is, having an event time included in the window left and right boundary, which are inclusive and exclusive, respectively. This can be easily answered under our assumption of tuples being sorted on their time step. Basically, the result for a window covering a certain period of time can be produced as soon as a tuple that has a timestamp equal to or greater than the right boundary of such period is received or processed. In this example, we have a window covering the period that goes from 8 to 9, and we want to count how many tuples we receive. We get a tuple at time 8:05 and set the counter to 1, a tuple at time 8:15 and set the counter to 2, and so on. As soon as we receive a tuple with a timestamp equal to or greater than 9, the tuple with timestamp 9:05 in this case, we can produce the result for the window that goes from 8 to 9, which is 4 in this case. We can then shift the window to 8:20, 9:20 in the example, and discard the tuples that no longer contribute to the window, also updating the counter. We have seen an example for an aggregate operator, but windows are used for streaming joins too. In this case, we have 2 input streams and 2 windows that will move forward according to the event time of the tuples being processed. This example shows how to define a time-based window in Flink. In this case, this is a tumbling window. That is a window that has the same value for the size and advanced parameters. And that's why we only specify the 5 seconds parameter in this example. As you can notice, this window is created for a stream after applying the key by function. We will get back to what this implies later on. But for now, we only need to know that in this case, a window will be maintained for each different value of the key by attributes observed in the stream. If we key by the vehicle ID, we will maintain one dedicated window for each vehicle we have in our data. Notice also that we are showing only some of the API provided by Apache Flink. Flink, as other SPs, allows users to define their own functions and operators. For an aggregate, we can, for instance, use the generic window function to implement our own semantics for the aggregate function. It is also important to notice that despite the fact that almost all SPs provide the same set of operators, each SPE might define its own variations of certain operators. At the same time, each operator can be implemented in different ways. If we look at stream joins in Flink, for instance, you can see that several types of stream joins can be defined. We are not covering in here how they differ, but please notice that the stream join I presented, and the one we consider here, would be the one that in Flink is referred to as the interval join, in which whether 2 tuples are compared or not depends on the distance between their timestamps. Now that we have covered basic streaming operators, we can move to an example showing how they can be composed in a streaming application. And this will be now covered by Bastian.
Hi, I'm Bastian, and I will now show you an example of how to compose basic streaming operators into a streaming query, and how to implement that query in Apache Flink. The example query builds on the dataset provided with the linear road benchmark. There is a large number of vehicles driving on a highway and wirelessly reporting their position, current speed, and the number of other data fields to a central server. Now, the query over this data that we want to answer is the following. Every 5 minutes of all vehicles that brake significantly, find the one that braked the hardest. I will now show you one way of how to compose the basic operators that Vincenzo just showed to you to answer this query. Here you see the topology of the query, and I will now walk you through the transformations and operations that are taking place inside it. First, a data source, not shown in the figure, provides the raw input tuples carrying all the fields of the raw data, shown as green triangles. Then, a map operator removes those fields not relevant for our query, and we're left with tuples carrying the vehicle ID, the timestamp, and the current speed, the red diamonds. Notice that the map operator multiplexes its output to two different downstream operators. To identify that the vehicle braked or significantly reduced its speed at all, we first establish a speed baseline for the vehicle. We do this by calculating its average speed over a certain period of time. Next in the graph, you thus see a stateful aggregate operator that every minute produces the average speed per vehicle of the last 2.5 minutes, and this output is shown here as a yellow square. Now, the output from the average and the map are joined on the vehicle ID. Aggregate tuples, yellow squares, are joined with those speed tuples, red diamonds, that come up to 1 minute later in time. Thus, we combine the speed a specific car is driving right now with the average speed it had up to a minute ago. This should help us determine whether the car slowed down significantly. The joint output is shown here as a superposition of square and diamond. Next, a filter operator admits only those joint tuples that have a high average speed and a low current speed, indicating the strong brake that we are looking for. Finally, a final aggregate produces every 5 minutes the one vehicle that braked the hardest during the last 5 minutes, as indicated by the ratio of average speed to current speed, which we call the brake factor. Having now schematically shown the query, let me show you how to implement this in Flink. Keep in mind that we provide the source code to this and all other examples in the repository. We begin by activating the source that will provide us with the raw input tuples and pointing the source towards the location of the input dataset. We have written a custom Flink source, and you can expect its code in the repository. Next, we implement the map function that removes unused fields of the input. You see that we simply specify here to return a new tuple carrying only the timestamp, the vehicle ID, and the current speed. Then we implement the speed average, which we do with Flink's apply operator. We first key by the vehicle ID, because the average should be performed per vehicle and not between several vehicles. Then we define the window over which we operate. Since we want the average speed of the last 2.5 minutes, the window size is 150 seconds. As we want to know this result every minute, we define the window advance as 60 seconds. Apply in Flink now gives us access to all the tuples inside the window. We simply iterate over all tuples in the window, construct the running sum of current speeds, and divide by the number of results. Lastly, we output the timestamp at the end of the window, the vehicle ID, and the average speed, which we just calculated. Then we join the streams of speed averages and current speeds with an interval join. The left stream is the stream of average speed tuples, and the right stream that of current speed tuples. We define the key on which to join them as the vehicle ID. Then we define the join window relative to the tuples from the stream of average speeds as from now to 60 seconds in the future. The join function, called process, simply produces a new tuple containing timestamp, vehicle ID, the current speed from the right stream, and the average speed from the left stream. Then we implement the filter. We simply define a predicate over the stream. The average speed needs to be above 20 and the current speed below 10. Lastly, we implement a second aggregate, this time to detect the maximum speed in a 5-minute window. This will then answer a query to know every 5 minutes which vehicle braked the hardest during the last 5 minutes. We use a tumbling window in which the window advance is equal to the window size. Again, we use the apply function, which gives us access to all tuples in the window. We simply search among these tuples for the one where the ratio of average speed to current speed is the largest and produce that tuple. And that's it. I will return in a few minutes to show you this code a bit more in action and pass back to Vincenzo.
After Bastian's examples, we can now move to the second part of the tutorial and discuss the causes of out-of-order data and the solutions we can find in the literature to enforce total ordering. Before we start, please notice that when I talk about order and out-of-order in the following, I refer to timestamp order and out-of-timestamp order. Before we discuss the role of event time, we need to spend some few words about how streaming applications are run by an SPE. What the user designs as a streaming application usually undergoes a series of transformations. This is true for many SPEs, from pioneer to modern ones. More concretely, the user usually composes operators into an abstract query. Then it specifies the parallelism degree for each operator, and the SPE converts the query accordingly. When the user instructs the SPE to deploy the query operators will be instantiated in a set of nodes. In this example, the operators are deployed at 5 nodes. Within each node, the operators could be deployed at one or more processes, and within each process, the operators could be run by one or more threads, although we do not show this here for simplicity. What is important to notice here is that operators deployed at different processes, potentially run by different threads within the same process, run asynchronously and communicate through producer-consumer queues. This transformation from an abstract query to the final streaming application can be found in Flink 2. I'm not going to cover in detail all the naming conventions one can find in Flink, but hopefully I can convince you that a query is also composed by operators in Flink, and that operators are run in a distributed, parallel, and asynchronous fashion by different threads and processes by Flink 2. The user defines tasks, which can contain a single operator or multiple operators chained together. The parallelism degree then defines how many instances, subtasks, are defined for each task. Each subtask is run asynchronously by a dedicated thread. When deployed, the tasks of a Flink program are deployed to task slots of one or more task managers. Each task manager is a separate process, defining one thread for each of its task slots. So far, we assume each vehicle was producing data in timestamp order, and such timestamp sorted data was fed to our operators. Is this a too strong assumption? In practice, yes. If we start focusing on the causes of out-of-order data, we can basically have two main reasons: sources themselves or more generally, asynchronous communication, especially in distributed and parallel executions. Let's start by focusing on sources themselves. You can find many related works that discuss reasons why data sources themselves could result in out-of-order data. The common example in this case is that of sources relying on protocols such as UDP. In the beginning of this tutorial, I mentioned that the Internet of Things and cyber-physical systems are prominent examples of big data applications. It is common in these setups to have battery-operated devices which need cheap communication protocols or have unreliable wireless networks and so on. What is interesting, though, is that even when sources can deliver ordered data, as we assumed in our previous examples, we can still observe data that is fed to streaming operators out of order. Let's start by looking at a specific example. Let's focus on a stream join operator. In the literature, the procedure used by stream joins to match tuples from two streams is known as the three-step procedure. Let's assume we have two producers. Each has a dedicated queue to forward its tuples to the stream join. Let's also assume that each producer delivers tuples in timestamp order. Notice that I use, in this case, the term producer rather than source, because this could be instances of other operators. Now let's assume that we have one processing unit, PU, that reads the tuples forwarded by the two producers and runs the stream join. This is the three-step procedure we consider in this example. For each incoming tuple T, the processing unit compares T with all the tuples in the opposite window using a given predicate P. It then adds T to its window and removes stale tuples from T's window. In this setup, we do not specify in which order the processing unit is expected to process tuples from the two consumers. If the processing unit arbitrarily interleaves tuples from the two streams, the output it produces can change in different executions. We can observe this in the following example. Let's assume this is our initial setup. We have two streams and two tuples in each stream window. In this first execution, we get tuple T3 in stream S and compare it with tuples T1 and T2 from stream R. In this alternative execution, nonetheless, we first get tuple T4 from stream R, and then we get a late T3 from stream S. In this case, tuple T4 causes its window to shift. As a result, when the late arrival T3 is processed, it will not be compared with the same tuples it was compared with in the previous execution, which means we could get less output tuples than before if the predicate matched for any of these two comparisons. I show you an example for a join, but this can be generalized basically for any operator in data streaming. That is, any operator fed data from multiple logical or physical streams can potentially observe out-of-order data. In this case, I use the term logical to refer to streams that could come from distinct sources and or carry different schemas, while the term physical refers to streams that are generated by parallel instances of the same operator. We discuss what this means in the following. To do this, I first need to cover how streaming operators are parallelized in SPEs. We start by considering two generic operators, A and B, as in this figure. When we parallelize operator A, it basically means that we deploy a certain number of instances of it, let's say M, to different threads. Each such instance is preceded by a merger and followed by a router. I will discuss in the following what is the functionality this to cover. Each instance can be run by a different thread. There could be several ways, actually, in which the instances are mapped to threads, as we show here. And there are also different ways in which threads are mapped to processes and processes are mapped to nodes. The logic and rules used to take such decisions can depend on the SPA you are using. Nonetheless, we parallelize operator A by deploying multiple instances, copies of it. And we do the same with operator B. At this point, we also create communication channels between the instances of A and those of B for exchanging tuples between them. Because of this parallel execution, which can also be distributed, because as I mentioned, the threads and processes running the various instances do not necessarily run on the same physical computer, data that was originally delivered in timestamp order can now reach operator instances out of order. Before I show you an example of this, please notice that the way in which we distribute tuples from the instances of operator A to those of operator B usually depends on the semantics of operator B. When we parallelize a stateful operator, we must ensure the routing is done according to its semantics. If, for instance, we want to parallelize an aggregate that counts how many reports are generated by each vehicle, we must make sure that all reports referring to the same vehicle are sent to exactly one instance of the parallel aggregate. In this example, we have that all reports from vehicle A should be sent to the first instance of the parallel aggregate. Notice that in practice, the routing is not based on static pre-allocations of keys to instances, also because we do not necessarily know which keys will be observed by a streaming application before the latter actually starts ingesting data. But the binding is done using hashed-based routing. Depending on the stateful operator semantics, the stream is partitioned into keys, and each key is assigned to one thread. The number of keys is larger than the number of instances running the operator in parallel, usually. As shown in this figure, the key domain is partitioned into these joint partitions, and each partition is assigned then to one of the instances. These are two examples of the Flink API that I showed you before. Here you can see that windows and aggregates are applied after invoking the keyBy method and on keyed streams. This is basically the way in which you tell how to parallelize the instances of a streaming aggregate and join it in Flink. If we now go back to our discussion about how operators are parallelized, we are ready for an example showing how it is possible to observe operators that are fed out of order data even when data sources forward timestamp sorted data. In this example, let's assume we get reports from many vehicles, and all these reports are delivered as a single stream of totally sorted tuples. We run a query composed by a map and an aggregate. The parallelism degree of the map is 2, and that of the aggregate is 3. In this example, tuples are routed to the instances of the map using round robin. Since the map is stateless, it does not really matter how we route its input tuples. Then the tuples fed to the aggregate are routed based on the aggregate's semantics. In this example, the aggregate runs per vehicle analysis, so the vehicle is used as the routing key. As you can see in this example, the tuples with timestamp 8 and 803 are sent to the first instance of the map, while the tuples with timestamp 07 is sent to the second instance of the map. Then all these tuples are sent to the same instance of the aggregate operator. If the second instance of the map is faster than the first instance, nonetheless, the tuples can still reach the first instance of the aggregate out of order. As you can see with this example, any operator with multiple streams, be them logical ones, as in the case of a join, or physical ones, as in this example, can observe out-of-order data when its producers run asynchronously. in parallel or in a distributed fashion. Notice that so far I did not specify what these merge operators are doing. In this case, they are delivering the tuples they receive in arbitrary order. As we discuss in the next part of the tutorial, nonetheless, they can be leveraged to actually prevent out-of-order tuples to be fed to other operator instances. But before doing that, I will leave again the floor to Bastian to show how what I just described can be observed in our Flink example.
Hi, I am back to show you how you can end up with out-of-order tuples in the example query that I introduced a few minutes ago. First, I will show you how some operators can inherently create disorder. To do this, we take our original Flink query and we insert an operator that prints the tuples in the order it sees them to a file. We simply call this the print to file operator. In the upper sketch, you see that operator added into the query. The remainder of the query is grayed out, and in fact, we are ignoring the downstream operators for now and truncating the query after the printing operator. Now, let's look at the source code in Flink. Here, you see part of our truncated query, and here is where we inserted the printing operator. All the tuples that pass the printing operator will be printed to the file we have indicated here. We will now execute the query, and we use a special data source that produces the data of only two vehicles. The reason for this is that we want to show you in a controlled way where the disorder is in the query, and you can take this example at home and play around with it. Let's run the query now and look at the produced output file, that is, the tuples that are forwarded by the filter. First of all, we see that both tuples seem to be semantically correct. So both correspond to events where a vehicle was reasonably fast and then slowed down strongly, as you can see by looking at these last two fields here. But let us look at the timestamp field, the first one. As you can see, the output is not in timestamp order. The reason for this is the order in which the interval join produces the outputs for different keys, and this actually upsets the total order of the output stream. The join first processes the second key with 1 and produces all matches, and then the first key with 0. As the output timestamp of the join is that of the later joined tuple, this can lead to disorder, as we see here. Thus, even simple standard operators can be a source of disorder, depending on how they were implemented in an SPE. Now, let me show you a much more common source of disorder. Let's say we decide to parallelize the map operator, such that we now have 4 parallel instances. The output streams of these 4 maps are unified again, and at that point we print the output to file. We see here in the sketch where we insert the printing operator. Again, we disregard downstream operators. So in Flink, here you see the printing operator. Let us now do a first run and just look at the tuples produced by the map with a parallelism of 1. As you can see from the first field, the tuples are in perfect timestamp order. Let's see now what happens when we increase the parallelism of the map to 4. In Flink, after every operator, you can define its parallelism degree. Here we had set 1, and we set this to 4. Now we execute the query again. as you can see now, total ordering is lost. The tuples seem to arrive in almost arbitrary order now. When the 4 output streams of the maps are unified, no sorting is taking place, and thus disorder is created. These were not 2 examples of disorder in a streaming system, with increased parallelism being a very common one. I now pass back to Vincenzo. Please keep in mind that you find all code in the repository for you to play around with and inspect.
Now that we have observed that out-of-order data can be fed to operators because of asynchronous parallel execution, the question we focus on is how to merge several timestamp sorted streams into one timestamp sorted stream. As we show in the following, this can be found in several papers in the literature, and let's go through some of the existing approaches. The first one we have is probably the most basic one. In this case, we can rely on dedicated producer-consumer queues in which we store the tuples forwarded by each producer. Periodically, or every time a new tuple is added by a producer, and if there is at least one tuple per queue, we select the one with the earliest timestamp, which will be the first tuple in one of the queues, and forward it to the following operator. In this case, the pseudocode is checking for special tuples, but this is not related to the merge sorting itself. A similar approach can be found in the Pioneer SPE called Borealis. We will actually get back to this example later on, since in this case the merge sorting is performed in the context of a solution for fault tolerance. As you can see in this figure, the query is preceded by a special operator called S-union, in this case, that merge sorts multiple input streams. In this case, though, the sorting is not performed on a per tuple basis, but rather periodically for buckets of tuples. Notice that in this case, the mechanism relies on special tuples, here called boundary tuples. These are the ones marked with letter B. Dimitris will later discuss more in detail what these special tuples are, so I'm not going into details right now. But the important point here is that, again, merge sorting does not need to happen on a per tuple basis if incoming tuples can be temporarily maintained in such buckets. An alternative approach is to rely on special data structures. In this case, the data structure is called ScaleGate. It resembles a skip list, a data structure in which data is kept sorted while being inserted. As you can see, each element is connected to the next element, but has also extra pointers that connect it to other future elements. On average, half of the nodes are connected with their peers that are 2 steps away. 1/4 of the nodes are connected with their peers that are 4 steps away, and so on. In this case, whenever a node is added, we keep adding pointers with a 50-50 probability. Notice that the fact that all tuples are sorted does not imply that they are ready to be processed. On the other hand, it is easy to locate which ones are sorted and ready to be processed, since these are the ones placed before any of the latest insertion from the producers adding tuples to such data structure. In this example, we have 2 producers, R and S. The latest tuple inserted by R has timestamp 10, while the last tuple inserted by S has timestamp 12. We do not know what the timestamp of the next tuple inserted by R or S will be, but we know R cannot insert a tuple with a timestamp lower than 10, because both R and S are delivering timestamp sorted streams. Similarly, S will not deliver a tuple with a timestamp lower than 12. Hence, all tuples before the first tuple that was last inserted by R or S, the one with timestamp 10 in this case, are not only sorted, but also ready to be processed. In summary, there are different options available in order to merge sort timestamp sorted streams into a single timestamp sorted stream. It boils down to the data structures that one wants to use and might also need support by means of special tuples. As said, this will be covered by Dimitris in the second part of the tutorial. One of the interesting things, nonetheless, is that we can choose who should pay the price for the merge sorting. If we use an approach in which the sorting is performed by who gives the tuples rather than who gets them, then we can achieve better scalability, especially when the cost of sorting is actually comparable with or higher than the cost of the subsequent stateful analysis. With this, we conclude the first part of the tutorial. Thank you.